are the dimensions. Let's see what units. Was it inches? Sheet of cardboard. Oh, feet. Feet. Are the dimensions in feet that give the max volume. And there we go. There's your second max-min word problem. We have not yet considered endpoints to the interval for our x values. I need to go back and look at this problem and consider the smallest that x could be. Remember, x is being cut out of two corners here, and the largest x could be. Well, here's a constraint on x, and here's a constraint on x. Okay, I did a quick change on you. Sorry about that, but I wanted to clean things up a little bit when we were considering these endpoints, and the white part of this paper was getting awfully covered with a lot of different colors of ink. So I want to clearly talk about what we need to look at and how we need to consider endpoints of an interval when we're doing these word problems. We've already said, here's one constraint on x, here's another constraint on x. We have our piece of cardboard laying here. If we made no cut out of any corner, that is one possibility for a value of x. It is a possibility that we don't make a cut. Here's the issue with that. If I include that as my left endpoint, I actually don't have volume. See if you can follow me through with this. What I have is I have length times width, but I have no height. But the minute I have any measurable value for x, I do have volume. And it could be max volume. So I actually don't have a closed interval in the context of this problem. If I include 0 in my interval, I don't have volume. But anything bigger than 0 will give me that third dimension, and I would have volume. So that's why I personally feel like this should be an open interval on the left. Now, as far as how big x could be, this is the biggest constraint on how big x could be. If I took this cardboard and I just folded it in half, if I took this and just folded it right on top of that, well, that would be the largest that x could be. Now, I could take and fold in this direction, and that would make x 2. But my problem is I can't take 2 out of all corners. I can only take 2 out of 2 corners. So that's why I say 3 is the biggest constraint. 3 is the smaller value. 3 is going to tell me how big of a cut I could actually get out of every corner. So if I take my cardboard and I fold it in half, and I put one piece of cardboard on top of another, then I don't have, I've got x as far as my right endpoint is concerned. I have an x value. The x value is 1.5, and that's my height. But then I no longer have a width. Now I'm dealing with length times no width times my height. So again, if I include 1.5 as the largest value x can be, I don't have volume. And in the context of this problem, my x values are going to be required to give me volume. I need 3 dimensions. So to me, I have an open interval here. I don't have endpoints to consider as far as I'm concerned in this problem. The last problem that we did as well, the first example on max-min, it was the same kind of thing. Is that to say we will never have to consider endpoints on a word problem? Not at all. That's not what I'm trying to say at all. But what I'm trying to say is it's a little more involved, and you have to think more in context of what you're doing as far as maximizing area or minimizing volume or cost or whatever. They are all problem specific. You are going to have to consider whether you have endpoints that you need to worry about at all. And to me, in this problem, we don't. Because if I was to have a closed interval, I would not have volume. I wouldn't have that third dimension, whether it was height or whether it was width or whether it was length. I wouldn't have the third dimension to actually give me volume. So there is endpoints. That's what we need to consider when we're talking about considering endpoints as critical points where extreme values could happen. Let's do one final example, and we'll consider endpoints. We'll look to see if we have endpoints that should be considered. I'll put it that way. A container in the shape of a right circular cylinder. Here is a right circular cylinder, and it's right in that the radius and the height meet at a right angle with no top. So this is open. And I'm making myself that note so I don't forget that later on down the line. I'm going to call this R, and I'm going to call that H. I like radius on circular things and height. That makes sense. I could equally call those things X and Y. But in this context, R and H make more sense to me. So, a container in the shape of a right circular cylinder with no top has surface area, I'm just going to call that capital S, capital A, of 3 feet square. What height, which I'm calling H, and base radius, which I'm calling R, will maximize volume? What height and base radius R will maximize the volume of the cylinder? This is a case where I am going to go on the hunt for my 2 equations. I'm going to go on the hunt for my relationship equation. I see H's and R's, and they've already told me that my optimization equation, I think I'm spelling it right this time actually, we'll see, is volume of a right circular cylinder, which is the area of the base times the height. So the relationship equation must come from another relationship between radius and height. This could be it. The surface area of my right circular cylinder, first of all, it's open on the top. So the surface area is going to consist of one base, there's the area of the base, and that is surface area. And then I'm going to add to that the sides. I need the surface area of the sides. Well, think of this as a rolled up piece of paper. And if we unrolled this piece of paper, the dimensions on that piece of paper would have height. If we're talking about surface area, we need width times height. Height is height, but width is actually this distance right here. If I unroll that piece of paper, the width of the surface area around a cylinder is the circumference of the circle that's formed when you fold that thing around into a circle. So the surface area of the base is pi r squared. The surface area of the sides is the circumference, that's the width, times the height. So there's surface area, and they tell me that's 3 feet square. So there's my relationship between R and H, and I'm going to use that to write my volume, my optimization equation, in terms of only one variable. I can see here that it's going to be much easier for me to solve this thing for H and put H in terms of R. So that's what I'm going to go about doing. I'm going to subtract this term from both sides. That's supposed to be an equal sign. So I'm subtracting pi r squared from both sides. I have moved this over to the other side and this to that side. And now I am going to divide both sides by that term. So H must equal 3 minus pi r squared all divided by 2 pi r. Now be really careful about trying to cancel pi and trying to cancel r. You have two terms in the numerator separated by a minus sign. Don't let your algebra steal points from you. Be really careful. Now I'm going to go down here, and I'm going to substitute that in our volume, our optimization equation for H. Now I can do some cleaning up. I have a pi in the numerator and a pi in the denominator. I have an r down here, and I have r squared there. So I definitely can clean the volume equation up. All I have out here is an r. So I'm going to distribute that r through the numerator. And I still have a 2 in the denominator. As a matter of fact, I can write this as a polynomial, which is going to make taking the derivative, because I'm after maximizing my volume, much easier. And I'm taking the derivative with respect to r. So the derivative of that term with respect to r is 3/2. Minus my 3 pops down front. I multiply it by pi over 2, and I reduce my power by 1. Now I want to know where that equals 0. Not gonna even look for where it might be undefined. That is a well-defined function. So I am going to subtract 3/2 from both sides and multiply both sides by -1. Hopefully you can go there with me. So r squared, I'm going to multiply both sides by 2 over 3 pi. Are we okay with that? R squared is 1 over pi.